Okay, we're now going to take a look at a couple of examples of orbital notation. Looking back at this diagram right here, you've got for your homework several small ones, but I'm going to use these bigger ones. Remember that they fill up in a certain order. And again, that is not an order that you need to memorize. I am going to show you how to do it tomorrow using the periodic table, but we're going to fill up in order of increasing energy. So when we start putting electrons in here, we'll start with a 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5b, 6p, 7s, 5f, 6d, 7p. And so they go in that order. And you can look up, I'm not a big fan of this at all. I can talk more about this later, but once I show you how to use the periodic table, it will definitely make a lot more sense to you. So let's go ahead and pick an element. And if we're looking at our periodic table, let's choose something somewhat simple. Let's take a look at calcium, okay? Notice that we're talking about a neutral atom of calcium that has 20 protons, which means we are going to assume that it also has 20 electrons. And so I'm just going to go ahead and write calcium down here, and we're looking to put 20 electrons. And the question is, why are we doing this in the first place? Because we've talked about electrons. They are moving very quick. They have quite a bit of energy, and this is just a prediction of where those electrons are located. This is probability, and this is just a two-dimensional way for us to represent where we think they are. We're going to count to 20 here. We're going to start down here, and this is an orbital. We said that we can fill them up one at a time. We can put 2 orbitals in each. So here we go. 1, 2. Each one of those arrows represents 1 electron, and there's 20 electrons. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. That's our orbital notation for calcium. I am representing those 20 electrons, and I'm showing where they are located more than likely within the atom. Notice that if I wanted to write this out, I would write this as 1s2 because that one is holding 2 electrons. Then I would write 2s2, again 2 electrons. Next I would go 2p6, 2, 4, 6, which is why that'd be at 6. 3s2 because it has 2 electrons. 3p6 is what I would write next. And lastly, 4s2 be the last one there, okay? If you think back to earlier whenever I was talking about magnetic spin, back over here, the reason that I'm putting them in opposite directions is because we said that no 2 electrons can move in the same direction. They're going to spin opposite of each other, which is why you see 1 arrow going up and 1 arrow going down there. Let's do one more practice. And we will take a look this time at just do selenium, 34. Again, that's 34 protons, and we understand that in a neutral atom of selenium, it would also have 34 electrons. So I'm just going to go ahead and write that down here. And we are looking to place those 34 electrons. You are always going to start at that 1s because that has the lowest amount of energy. And let's just start counting. Notice that they do fill in a pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 4s to 3d. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 4 more to go. 31, 32, 33. Come back over here, 34. And so I see that I actually have 2 orbitals here open. And now you're probably wondering, why does she go through and do all with the upward spin and then go back and fill them in? That is because of some of your rules. You've got 3 rules. You've got the Heisenberg uncertainty principle, you've got the off-ball principle, and you've got Hund's rule. And we are going to talk about those when we move into electron configuration. Electron configuration is when you physically write out those energy levels and how many are in each orbital within each sublevel. So this big picture that you see here is called orbital notation. It's when you use those spaces and use the arrows. This is called electron configuration. This is what we're going to learn how to do tomorrow using the periodic table, and that is what will be tested on your EOC. If you were writing the electron configuration out of selenium, you would do the same thing. You would start by saying 1s2. And again, why am I putting that 2 there? Because there's 2 electrons in that 1s orbital. Then I would come up here 2s2 because I see those 2 electrons. 2p2, 2p4, 2p6. So I write 2p6, 3s2 because there's only 2 electrons there. 3p2, 3p4, 3p6. Within this 3p, there's a total of 6, so I'm going to write 3p6. 4s2, 3d10, 3d2, 4, 6, 8, and 10. So we'll write 3d and then a 10. And then right here is where 4p2, 3, 4. So on that last one, it's not completely full. It only has 4. It actually has space where it could take in 2 more electrons if it needed to. Again, that's called electron configuration, and we will look at that more specifically tomorrow. This top part that you see here, that's your orbital notation. That's what we're more focused on today.